Right, y'all, Daryl Eberry Jr. back. Everything should be fixed and working properly. We have the chat up. Hopefully the audio is fine. Y'all can let me know. It seems fine on my end. And we'll go ahead and continue with where we left off. As I said, I was going to do these perturbations here. So perhaps I'll clean up the graph a bit. So we'll see what these perturbations look like. So we'll basically compare our intuition to what we think it should be. Now, here, of course, it looks like it's symmetric over the diagonal. Um, Given that if I was to draw a diagonal here and flop it, it's the same. Even if I draw a diagonal this side and flop it, it's the same. So let's take a look from both perspectives. So checking the answer, actually, I don't see the one for B. Why don't we calculate it? See what it looks like. So basically, we can do this same integral here. But now it'll be more complicated. So we'll have this. It would be 0 to a over 3, 0, and would also be plus a over 3 to a. So those are the realms that the perturbation are in right now, and it's actually 2a over 3. So this would give us 1/2 times the integral of cosine negative phi x over a dx minus cosine 3 pi x over a dx. And this would be 0 to a over 3, 0 to a over 3. And it'll be the same thing with a plus. to a over 3 to a to a. So let's see what this looks like. We have 1/2, and this would be sine negative pi x over a negative a over pi minus sine 3 pi x over a over 3 pi and would have the same thing here, except the bounds would be a over 3, 0, a 2a over 3. So this would give us 1/2 so a over 3 negative a over pi and sine negative pi over 3 minus a over 3 pi sine pi. Oh, there's going to be minus 0 plus 1/2 negative a over pi. There's going to be sine negative pi minus a over 3 pi sine. A is going to cancel, the 3 is going to cancel, 2 pi minus 1/2 negative a over pi sine. So the a cancels, 2 pi over 3 with a negative minus 3 over 3 pi sine. The 3 cancels, the a cancels, so that's 2 pi. So sine of pi is 0, sine of negative pi is 0, this is 0, this is 0. So we're left with 1/2 negative a over pi, and sine is odd. So negative is the negative of that. So I could just put sine pi over 3 minus a over pi sine 2 pi over 3. And again, I'm just keeping this negative here, but distributing this negative from the negative sign, distributing this negative from the negative sign. So it should give us 0 again. And I'm going to extract this. So now I have sine sine pi over 3 minus sine 2 pi over 3, and we do get 0. Wherever the diagonal matrix is 0, it's symmetric over the diagonal. We don't have to consider the diagonal. It takes a long time to do that. I think the only one that won't be symmetric over that diagonal, this one is, this one is, this one seems to not be. And this one seems to be. So let me see what I did last time. So I'll take a look real fast and see what my records show. So is diagonal. So AC and D are diagonal. B is not diagonal. So I think the solutions are saying B are not diagonal. Perhaps because it's diagonal only in one direction. Um, you know, only integrated the X for this one. That would be diagonal at Y as well. Let me check something. So WAB and WBA equals 0, then it's diagonal. So looking at this, So a symmetric on the x-axis. Right. And check one more thing. So I think what I'm going to do is check these integrals again. Typing them in. So I'll check this one here. I'll move it Y. Right. Let's confirm that this is 0. believe the calculator is still saying it equals 0. Let's try the second one. Here we have that. Saying this one does give a value. Right. So let's see what I did here. Maybe it's because this one equals 0 on the x. I need to try the y one as well. So that's just saying neither of them equals 0. So let's see what I did wrong with this integral here. Definitely need to hear more about this problem. I'll just ask about this one later. Next problem. And by the way, the solution says A, C, and D. Which is correct. I think I guessed on B the first time. So let me share previous reasoning. as a shortcut before we move on. So seems good though to be able to do the integrals. But I guess we just don't have enough time to do them on the exam. Our previous reasoning was this from way back at the beginning of the semester. I think I need to plug up my pad. Give me a moment here. Right, and this works. I have it plugged directly into the outlet, which I don't normally like to do, but as long as there's not a lightning storm, I should be okay. But if I looked at it before, the WAB, which is this one here, with the boxes in the middle, what the integral looks like, the bounds are symmetric over a symmetric bound. So it is 0, because the signs have different values. M equals not N. For the second one, which is this one, is what the integrals look like. 0 to a over 3 for both x and y, and then a over 3 to a for x and y. And that one seemed too complicated to think about, so I just assumed that that one was not symmetric, which was the right answer. This is the one where the box is here, at least the perturbation. So we have on the x-axis, it is symmetric. So it'll be 0. And one thing that trips me up a little bit is that the perturbation is only on half of the x-axis for this one. I mean, so this is y, this is x. But it doesn't extend all the way up here, so x here, and this one is clearly either along the whole x-axis it is symmetric, and on the whole y-axis it's just equal or not. So I had A, C, D. So putting it in the calculator, that confirms that B gives us a value, so it's not uh, good. See what it says for one of the other ones real fast. A over 4. So I'll check the third one. All right, so that one is symmetric, so it's 0. And welcome those who are watching. Be sure to drop a line. Let me know if you have any questions or comments. The one thing I'm thinking about now is why we don't take into the account that the perturbation is from A over 3 to 2A over 3 only when y is from 0 to 0.5. So I see. Well, technically, we would only integrate the y from there to there anyway. So we're looking only at the perturbation for this part. All right, makes more sense. I shall go to the next problem. So the next problem says right? So we're doing perturbation theory still, non-degenerate states. So just reminding ourselves of the derivation. So if we're doing perturbation theory, the default uh, so this is without a perturbation, the Hamiltonian eigenfunction and eigenvalue, you're going to have a perturbed function, Hamiltonian. We have h in H naught plus H prime it's a new, we have a new wave function, which is psi n naught plus lambda psi n1 plus lambda squared psi n2. And we have a new energy, which is En naught plus En1 plus En squared, and so forth. So if we wanted to get the perturbed one, it'll be H lambda equals En lambda. And if we only go on to the first order, this will be H naught plus H prime naught plus lambda 1 equals En naught plus lambda En1 lambda n naught plus lambda psi n1. So if I distribute these, H naught n naught plus H naught lambda psi n1 plus H prime psi n naught plus, that's going to be squared, so we could ignore that, n naught psi n naught plus En naught lambda psi n1 plus lambda n1 psi n naught, and again that's squared, so we could ignore that one. And these are simply the default, so we could ignore this. So we have what the book has to start with, H naught psi n1 plus H prime psi n naught equals En naught lambda n1 plus En1 lambda n naught. So the next step to find En1 the original way is to multiply by the psi n naught ket. We end up with psi n naught, the psi n naught bra, psi n1 plus psi n naught H prime psi n naught psi n naught. So we have that written out, and this is just a constant, so it'll come out to the front, and m equals not n, so this would be 0. This is just another number, so it comes out to the front, and these are the same, so this equals 1. And this one is just a constant, so it comes out to the front. These are not the same, so it equals 0. So we have En1 equals psi n naught H prime psi n So that's easy enough. And another way we can do it is we can, from this point here, recognize that psi n1 is going to be the sum, where m equals not n, of cm psi m naught, which I did recently on my other channels, pretty long. Welcome who's joined. Be sure to drop a line. So I can actually substitute this there and here. Well, that's 0, so I'm not going to multiply that anymore. We're going to substitute specifically, it'll substitute here and here. And when we do that, and L equals N, then we get the same thing. So I think the main thing to remember is this: psi n1, when we solve for psi n1 as a ket, we're going to equal the sum m equals n of cm psi m naught. And we can substitute that n into that part of the equation. Let's see what the next problem is. Isaac Klutz-Gordon. So give me a moment. I'll get a hold of one of the Klutz-Gordon tables really fast. Hey, what's going on, Catherine? How you doing? Getting in a bit more detail today. Working on what I'll do in general overall tonight on the other channel. I can use all the quantum practice I can get. I actually need to keep track of the time because uh, we're going to have our office hours coming up. I'm writing down what I'm going to ask about at 2, so I still have plenty of time. So I'm going to finish these first round of questions. Doing good as well. I'm starting to feel better about the exam. That's right, I'm going to do thermal tonight. I'm starting to feel better about the quantum exam. I'll finish working on this quantum stuff and have something prepared for Thursday night on the other channel. I'll do thermal tonight, but feeling a whole lot better about the thermal than the quantum, but thankfully the quantum is not until Monday. So we'll have a few days. All right, let's see here. Last problem on this particular round. So right now, by the way, Catherine, it's what? Uh, is it 5 a.m. by you just about? 6 a.m.? 5 a.m.? You 5 are ahead of me or 5? No, you 5 after me. So it's 5 p.m. It's almost 5 p.m. by you right now? I didn't even know you were in like overseas. 5 p.m. Ah, awesome. So this next problem is about the Klutz-Gordon table. I'm going to get a hold of the file for from the Klutz-Gordon that we're given, and this would be a different Klutz-Gordon than we looked at. So I think on the other channel, I believe I did briefly part of a Klebs-Gorton. So I'll look to do a more complete one this time. Found a better way to plug in my pad, by the way, even though it's directly into the wall. I do like to avoid that so it doesn't get like an electric shock. Oh, yes. Let me put the screen back on. Thanks. I forget to do that less than I used to, but I still forget sometimes. So the idea is going to be we're going to use the Klebs-Gorton table of coefficients, and we're going to look at the 2 1/2 section, which I actually don't see here. Two 1/2. All right, so I'm going to have to pull up a Klebs-Gorton table. Yeah, they're ugly. Thankfully, they're everywhere, seems like. I imagine the physicists who really do this uh, can't imagine have to calculate everything over and over again. So what's the best way to do this? I think I might actually add the table as another image. Um, Maybe that'll be the most efficient way to do this. And this one is actually a pretty good table that actually gives some background. So I'll put this up on the screen as a new image. Mm, Almost there. I hate when this happens. Oh, that's because I maximized the window. But you can't have anything maximized in front of the whatchamacallit where it does that. And I guess this will go here. Almost there. Boom. And I'll add this. And I guess I should technically go to my regular share screen. Hopefully the horizontal window still makes looking a bit better. Thanks for the link, Catherine. I appreciate it. And here will be the image. All right. So the idea is let me put this, let's see. Oh, well, it's not going to hurt to have it at the top momentarily. No, these are not Fibonacci sequences as much as far as I heard of them. So this is not at all any kind of mathematical concept. This is literally experimental results of how these quantum components mixed up together. So if I look at so right now I'm looking at the 2 by 1/2 table. And in my office hours yesterday, this is how the professor basically explained it. So when you're looking at this table, and I'll zoom in on the 2 and 1/2 one. So you can see it says 2 cross 1/2 on the top left right there. So what that's saying is we have 2 angular momenta of subatomic particles that are being mixed together. Now, the fact that one is 1/2, I suppose there might be other more advanced particles that uh, have a 1/2 spin, but all we know about right now is basically electrons. So the fact that it says 1/2 means that that has to be talking about an electron angular momentum. And where it's talking about a 2, it has to be something with an integer, either something with an integer spin or a whole bunch of half integer spins that adds up in such a way to where it equals up to being a 2. So these are this is going to be spin, at least at the level of that I'm at, like an electron spin. And this will be something like the L angular momentum, because we know from the other channel that if we have an energy, it's going to be an integer. Let's say it's going to have to be at least 3, because L is going to be 0, 1, and 2, because L is going to be from 0 up to n minus 1. So we know if this is a particle with, let's say, a whole spin, uh, it could be something with whole spins, or it could be a particle with L of 2. So it's going to be something with an energy of at least 3. So something with an energy of at least 3 that's mixing with an electron, and the electron has its spin. This has its L equals 2, and these are going to blend in some kind of way that is going to output something, and the result is going to be what we see in the table. So that's where we're at now. I'm going to go ahead and add this back. I'm going to try to keep this table on the screen somewhere. And I'll crop it so that we see exactly what we're looking at. So why don't we do 40 on the left? I guess that's 400 on the left. And 100 on the top. Actually 75 on the top. I like that reminder there. 450 on the left. And I think that's sufficient. Now we have our table. We have everything we need. So what I'm going to do here is, so that's the general of what it is. And if you look at the top there, it actually gives you the key where we have our table. This is going to be the J, this is going to be the M, and this is going to be M1, and it's going to be M2. And the professor was saying that it doesn't really matter what this stuff is. We could just remember that J is going to be L plus S, and M is going to be negative plus minus L, or plus or minus L or J or even S. Everything has a M, which is like a subcategory of that. But we'll go ahead and look at the J's right now. Let's see what other detail they might want us to specify before I move on to actually writing out what the table is. So I talked about what 2 and 1/2 talks about. So Oh, and I already answered two parts of it. So we talked about what two and one half is the blending of the angular momentums of a one half something and the integer something with the integer of two. We talked about how it can be, for instance, an electron with a one half spin mixing with something with a particle with an L of at least two. So it has to have an energy of at least three. So or n number for at least three to have an L of at least two, or it can have an n of five, which means it has an L 0, 1, 2, 3, 4, but we could still only be talking about the L equals 2 level. So that's basically the physical situation it can be of, and how we actually use the table to write down the components. So L is basically in one regime, and the M's are in another regime. Let me move this a little bit. So basically, this shows us how the J and the capital J and capital M angular momentum, how that breaks into the subcategories of angular momentums and back. So these little m's, it shows us how it combines with the big S and the big L. And so let's actually look at this, and it'll make more sense when I actually do one. So let me expand this a bit and put this here. So I have, for the 2 1/2, I can say that we have the state 5 halves, 5 halves starting at the top. And this is going to equal square root of 1 and 2 and positive 1/2. So this is a state with a J of 5 halves, M 5 halves, and the way the sub M levels mix together. This could be, for instance, M for the big particle of 2 and ms of 1/2. So that's one way to look at that one. And this is the top corner on the left. So it's hard for me to draw on this image here. I don't even know if I can draw on the image where it is right there. But I suppose I can edit the actual image and it'll show up there to help clarify it. So let's try that. So what I just did just now, that would have been marker, boom, yellow. So that would have been this one. Oh crap. I guess I need to lighten this thing a bit. All right, well, guess I'll just circle it. Gotta have been that one there. Let's see if it works. Yes, it works. So you can see where I circled. That's the one that I did just now. Let me increase the width of this. So now I'll do the next one. So the next one says we have J of 5/2 and M of 3/2. And that's going to equal square root 1/5. And that's going to be the M1 of 2 and the M2 of negative 1/2 plus square root of 4/5. And that's going to be the sub M1 and sub M of 1/2. So that was this one here. And what did I try? The calligraphy pen. So that was this one here. Boom. So that's what we just did. So you can see the 5/2, 3/2 here. The thing that's in the middle box is always a square root because it ends up being a probability. And then the ones on the right are the sub values there. So let's do the next one. So the next one would be J 3/2, capital J, and capital M of 3/2. I believe that's positive. I think my ink wrote it over. Yeah, it's positive. And that's going to equal square root of 4/5. And we're going to get our +2 minus 1/2. And there's a minus here, square root of 1/5. And 1/1/2. So notice that now I've done all 4 of these here. And notice that the negative that's in front of the 1/5, that goes in front of the coefficient. So it makes that whole thing negative. So let's say, for instance, I wanted to, it's hard for me to think of a problem because I just don't think I understand it all well enough to think of an accurate problem. So this might not be quite accurate. But let's say I wanted the probability of finding uh, a sub m2 and -1/2. Then I could just take this coefficient and say Cm, when I say C sub m equals square root of 4/5, and Cm squared gives us 4/5. So it's basically a probability of 4/5 if I have a capital J of 3/2 and capital M of 3/2. If I have, and the physicists know how to do this, they can take particles and put it in the state they want. I don't know how to do that yet, of course. But if I put a particle in a J equals 3/2 and an M equals 3/2 state, and I want the probability of getting either a uh, little sub m 1/2 and spin of -1/2, or a sub m of 1 and spin of +1/2. 4/5 of the time, I'll get this configuration, and 1/5 of the time, I'll get this configuration if I have a particle put in a 3/2 state. And this stuff is important when it gets to things like there was an experiment that our professor told us about. I believe these people even won a Nobel Prize for this one. Um, what they wanted to do was so hydrogen is very particular as an element, and there are some states of hydrogen that respond in very unusual ways, just like how oxygen is sort of like a magnet, like oxygen in itself, like the way oxygen is configured, for one, is usually O2, and the way the atoms are connected, and the way the oxygen molecules, it has like 16 electrons total, and the way the valence electrons sit when the oxygens connect to each other, they form a dipole. And when you get oxygen cool enough, it becomes a magnet. Like, there's a quirk of oxygen that if you get it cool enough to where the particles are close enough together, it forms a magnet, and it actually can attract things, and you can attract it with a magnet. And there was one image professor showed where there was liquid oxygen in a balloon, and there was a magnet, like a strong magnet right here, and the balloon was going like this. And you can see that it was liquid in there. Like if you ever saw a balloon with liquid nitrogen, and of course, like there's whole, you know, the little steam condensation everywhere because there's ice everywhere. But the balloon of oxygen is like pulled towards the magnet. You can see it is cooled down. But hydrogen has other perks as well. And but the atoms have to be in a certain state in order to see these perks. So the scientists had to find a way to preferentially pick out which states hydrogen was in. So then they was able to get a whole bunch of these hydrogen in a certain state. Like let's say a whole bunch of hydrogen where there's a capital J3 over 2 and capital M3 over 2. And since they had a bunch of hydrogen in their state, they was able to do a bunch of experiments like, you know, see what the preference see what the preference will be for certain subatomic components. But suffice it to say, it was able to configure a way to get this element. And it might not have been hydrogen, whatever element it was. They got so a whole lot of them configured in a certain way. They were able to do a specific type of experiment to determine a certain quality of that element. And I believe they won the Nobel Prize for it because it's something that's utilized. All of this stuff is like some things are utilized a whole lot. That's that. And the process goes the same. So in this way, we can actually um, write down every you know configuration of the different states that you will see in nature from the combining of certain angular momentum of certain subatomic particles. So that's pretty much all we had to do for that problem. Um, when I originally did the first time I did the problem, I, that's what I basically did. Like I used the Clebsch-Gorton table and just wrote out a few of those and explained what it was, and uh, and that was that. And Catherine says, "Ocean is fascinating. Can you get is that O8? Okay, I didn't even know that. You saying you can get oxygen with 8 electrons? Or you mean 8 oxygens binded together? So you mean you can get like 8 oxygens like this? I don't know how they will be bound, but it'll be 8 of them stuck together. Oh, interesting. I can see that. Pretty sure you can do that with carbon. Carbon is like, well, I guess we all know carbon is like the foundation of our being, I guess. So carbon seems to bond with a whole bunch of stuff. Yeah, that's pretty cool. Oxygen sounds fun. So what I'll do, I can't really say I'm versed on the mid stuff. But I could try to do one of those problems. Yeah, I gotta watch the video. The professor went over he went over the solutions to this exam, but I did like absolutely horrible on this exam. Crazy horrible. So I'm gonna have to research the stuff for the middle portion of the exam. But what I'll do, I'll make sure to have enough of it understood so that for the Friday quantum stream, the Friday evening quantum stream, I'll talk about that stuff. But tonight I'll talk about some thermal stuff. So I'll come back tonight and I'll do the I guess it'll be from chapter 5 through chapter 7, like chapter 5, 6, 7 level thermal stuff tonight for the our regular problem solving screen. And then I'll be prepared to do some higher level quantum 2 stuff. I just gotta learn what to do today and tomorrow. So, but awesome, Catherine. Thanks for joining. So it's been what? It's been about hour, almost an hour, 15 minutes. So I think it's a good time for a break. And I'll be back tonight, just like today. I'll try to do a long marathon. I'm a lot better with thermal than quantum at the moment. So I'll try to do like a 2-hour marathon tonight. I guess technically it'll be 6, 7 hours from now. About 7 hours from now. I think I should be back by then, give or take, between 6 and 8 hours from now. And thanks to all who watch. Thanks to all who's watching now. Don't be shy about dropping a line. Let me know if you have any questions or comments. And I'll see everybody tonight. It'll be on my other channel, by the way. Those who are watching now, just go to the website I have at the top right there, darrellliberajr.com, and go to the personal YouTube. And I'll be there in about 6 or 7 hours, and I'll do some problem-solving marathon where I just go through a bunch of problems in thermal. And on that same channel tomorrow night, I'll do some quantum problems. But I might be back here again in the daytime tomorrow, trying to figure out the quantum stuff like I was doing today. So thanks everybody for joining and watching. Thanks Catherine as always for being here, and look forward to seeing you tonight as well. Y'all have a good evening.